Alright guys, very happy to meet you again. I'm your friend InsideXO. Today in this video we will talking about the Chapter 8, Learning Signal and Ignoring Noise, Introduction to Regularization and Batching. In this chapter we will learn three part of sense: the overfitting, the dropout, the bit gradient descent. With 4 parameters, I can fit an elephant, and with 5, I can make him waggle his trunk. 3-layer network on MNIST. Let's return to the MNIST dataset and attempt to classify it with a new network. In next several chapters, you'll learn that neural networks model correlation. The hidden layers, the middle one in the 3-layer network, can even create intermediate correlation to help solve for a task seemingly out of mid-air. How do you know the network is creating good correlation? When we discuss the stochastic gradient descent with multiple inputs, we run an experiment where we freeze one weight and then asked the network to continue training. As it was training, the dots found the bottom of the balls. As it were, you saw the weights become adjusted to memorize the error. When we froze the weight, the frozen weight still found the bottom of the ball. For some reason, the ball moved so that the frozen weight value became optimal. Furthermore, if we unfroze the weight to do some more training, it won't learn. Why? Well, the error had already fallen to 0. As far as the network was concerned, there was nothing more to learn. This begs the question, what if the input to the frozen weight was important to predicting baseball victory in the real world? What if the network had figured out a way to accurately predict the games in the training datasets? Because that's what the networks do. They minimize error, but it somehow forgot to include a valuable input. Unfortunately, this phenomenon, overfitting, is extremely common in neural networks. We could say it's the archnemesis of neural networks. And the more powerful the neural network's expressive power, more layers and weights, the more prone the network is to overfit. An everlasting battle is going on in research, where people continually find tasks that need more powerful layers, but then have to do lots of problem solving to make sure the network doesn't overfit. In this chapter, we are going to study the basics of regularization, which is the key to combating overfitting in neural networks. To do this, we'll start with the most powerful neural network, 3-layer network with ReLU hidden layer on the most challenging task, MNIST digit classification. To begin, go ahead and train the network. As shown next, you should see the same results as those listed. Alas, the network learned to perfectly predict the training data. Should we celebrate? Here's the code that we can save from this book. We import SYS, NumPy as NP. From carrots that datasets import MNIST. We get our xtrain, ytrain, xtest, ytest arrays from MNIST.load data function. Then we take the first 1000 elements from those arrays as our training data, and we convert the value to one-hot labels. We will talk about that later, about the one-hot array. For IAL enumerate labels, we calculate the labels. We do the same thing with the test datasets. Then we set the read number. We define the ReLU function. The ReLU normally do things like returns x if x greater than 0, return 0 otherwise. The ReLU2deriv function, it is also an activator function. It returns 1 for input greater than 0, returns 0 otherwise. Then we define our super parameters alpha, iterations, hidden size, pixels per time, number of labels. You may ask why there we have to give it the number of 10. It is simply because all we got the number that we got is from 0 to 9. So the length of that number is 10. The length of that number series is 10. Then we define our weights with real numbers. Then we do the same thing with 3 layers calculation that we have already very familiar with in the previous chapters. Well, that was easy. The neural network perfectly learned to predict all 1000 images. In some ways, this is a real victory. The neural network was able to take a dataset of 1000 images and learn to correlate each input image with the correct label. How did it do this? It iterated through each image, made a prediction, and then updated each weight ever so slightly so the prediction was better next time. Doing this long enough on all the images eventually reached a state where the network could correctly predict on all the images. Here's non-obvious question: how well will the neural network do on an image it hasn't seen before? In other words, how well will it do on an image that wasn't part of the 1000 images it was trained on? The NNIST dataset has many more images than just the 1000 you trained on. That's right. In the notebook from the previous code are 2 variables, test images and test labels. If you execute the following code, it will run the neural network on these images and evaluate how well the network classifies them. If the condition was met, we will do this test. So actually, the layer 0 is the input layer. So in the most original thoughts, it can be the input of the data. So you can just put the images to you can just treat that image as the first layer. Then you use a matrix production function to get the result by using the weights. Then you calculate the error. It's all the same. The only thing that's different is that you don't have to update your errors in this time because you are trying to do a test instead of training. The network did terribly. It predicted with an accuracy of only 70%. Why does it do so terribly on these new testing images when it learned to predict with 100% accuracy on the training data? How strange. This 70% number is called the test accuracy. It's the accuracy of the neural network on data the network was not trained on. This number is important because it simulates how well the neural network will perform if you try to use it in the real world, which gives the network only images that it hasn't seen before. This is the score that matters. Memorizations vs. Generalization. Memorizing 1,000 images is easier than generalizing to all images. Let's consider again how a neural network learns. It adjusts each weight in each matrix, so the network is better able to take specific inputs and make a specific prediction. Perhaps a better question might be, if we trained on 1,000 images, which it learns to predict perfectly, why does it work on other images at all? As you might expect, when the fully trained neural network is applied to a new image, it's guaranteed to work well only if the new image is nearly identical to an image from the training data. Why? Because the neural network learned to transfer input data to output data for only very specific input configurations. If you give it something that doesn't look familiar, it will predict randomly. This makes neural networks kind of pointless. What's the point of a neural network working only on the data you trained it on? You already know the correct classifications for those data points. Neural networks are useful only if they work on data you don't already know the answer. As it turns out, there's a way to combat this. Here I have printed out both the training and the testing accuracy of the neural network as it was training every 10 iterations. Notice anything interesting? You should say a clone to better networks. Okay, from this list of data from this table, I could say if we stop at the maybe 30 iterations, 30 times 10 iterations, the test accuracy could be something like 0.8. It's much better for compared to the following test accuracy. So we'd better stop when we get the best test accuracy. That's my opinion. Overfitting in neural networks. Neural networks can get worse if you train them too much. For some reason, the test accuracy went up for the first 20 iterations and then slowly decreased as the network trained more and more, during which time the training accuracy was still improving. This is common in neural networks. Let me explain the phenomenon with an analog. Imagine you are creating a mode for a common dinner fork, but instead of using it to create other forks, you want to use it to identify whether a particular utensil is a fork. If an object fits in the mode, you'll conclude that the object is a fork, and if it doesn't, you'll conclude that it's not a fork. Let's say you set out to make this mode, and you start with a wet piece of clay and a big bucket of three-pronged forks, spoons, and knives. You then press each of the forks into the same place in the mode to create an outline, which sort of looks like a mousy fork. You repeatedly place all the forks in the clone over and over, hundreds of times. When you let the clone dry, you then find that none of the spoons or knives fit into this mode, but all the forks do. Awesome, you did it. You correctly made a mold that can fit only the shape of a fork. But what happens if someone hands you a four-pronged fork? You look at your mold and notice that there's a specific outline for three thin palms in the clone. The four-punched fork doesn't fit. Why not? It's still a fork. It's because the clone wasn't molded on any four-pronged forks. It was molded only on the three-punched variety. In this way, the clone has overfed to recognize only the types of forks it was trained to shape. This is exactly the same phenomenon you just witnessed in the neural network. It's an even closer pattern than you might think. One way to view the weights of a neural network is as a high-dimensional shape. As you train this shape molds around the shape of the data, learning to distinguish one pattern from another. Unfortunately, the images in the testing dataset were slightly different from the patterns in the training dataset. This caused the network to fail on many of the testing examples. A more official definition of a neural network that overfits in a neural network that has learned the noise in the dataset instead of making decisions based only on the true signal. Alright, where the overfitting comes from? What causes neural networks to overfit? Let's alter this scenario a bit. Picture the fresh clean again, unmolded. What if you pushed only a single fork into it, assuming the clone was very thin? It wouldn't have as much detail as the previous mold, which was imprinted many times. Thus, it would be only a very general shape of a fork. This shape might be compatible with both the 3 and 4-punched varieties of fork, because it's still a fuzzy imprint. Assuming this information, the mold got worse at the testing dataset as you imprinted more forks because it learned more detailed information about the training dataset it was being modeled to. This caused it to reject images that were even the slightest bit off from what it had repeatedly seen in the training data. So what is this detailed information in the images that's incompatible with the test data? In the fork analog, it's the number of punks on the fork. In images, it's generally referred to as noise. In reality, it's a bit more nuanced. Consider the following two dogs pictures. All those text or explanations are just trying to speak one thing. That is, if you train your neural network too many times on a dataset, it will overfit. The overfit means that it will try to memorize all those details in that training dataset. And if they did that, if your neural network did that, it will not be able to recognize the same thing you thought it is, and instead it will try to reject anything that has a little bit difference than the training data. You can consider these two dog pictures in here. Everything that makes these images unique beyond what captures the essence of dog is included in the term noise. In the picture on the left, the pedal and the background are both noise. In the picture on the right, the empty metal black glass of the dog is a form of noise as well. It's really the edges that tell you it's a dog. The metal black glass doesn't tell you anything. In the picture on the left, the middle of the dog has the furry texture and corner of the dog, which could help to the classification for you. So which could help the classifier correctly identify it. How do you get neural networks to train only on the signal, the essence of a dog, and ignore the noise, other stuff at the same picture? One way is early stopping. It turns out a large amount of noise comes in the fine-grained detail of an image, and most of the signal is found in the general shape and perhaps corner of the image. The simplest regularization, early stopping. Stop training the neural network when it starts getting worse. How do you get a neural network to ignore the fine-grained detail and capture only the general information present in the data, such as the general shape of a dog or an digit? You don't let the network train long enough to learn it. In the fog mode example, it takes many folks imprinted many times to create the perfect outline of a three-punched fog. The first few imprints generally capture only the shadow outline of a fog. The same can be said for neural networks. As a result, early stopping is the cheapest form of regularization, and if you are in a pinch, it can be quite effective. This brings us to the subject this chapter is all about, regularization. Regularization is a subfield of methods for getting a model to generalize to new data points instead of just memorizing the training data. It's a subset of methods that helps the neural network learn the signal and ignore the noise. In this case, it's a toolset at your disposal to create neural networks that have these properties. The next question might be, how do you know when to stop? The only real way to know is to run the model on data that isn't in the training dataset. This is typically done using a second test dataset called a validation set. In some circumstances, if you used the test sets for knowing when to stop, you could overfit to the test set. As a general rule, you don't use it to control training. You use a validation set instead. Industry standard regularization dropout. The method randomly turns off nerves, set them to zero during training. Okay, I don't know that. At the beginning or in most of the time when I do the deep learning, I would think about the dropout as a dropout. Like if I set the dropout to 50%, I would say, oh, I will drop out the 50% of those information to our network or to the next layer of that neural network. I wanna think it as, set them to zero. I wanna do that, but now it turns out, what the dropout does is to set them to zero, set the nerves to zero or the weights to zero. I don't know. This regularization technique is as simple as it sounds. During training, you randomly set neurons in the network to zero, and usually the delta on the same nodes during backpropagation. But you technically don't have to do that. This causes the network to train exclusively using written subsections of the neural networks. Believe it or not, this regularization technique is generally accepted as the go-to state-of-the-art regularization technique for the vast majority of the networks. Its methodology is simple and inexpensive, although the intuitions behind why it works are a bit more complex. Why dropout works, perhaps oversimplified. Dropout means a big network acts like a little one by randomly training let subsections of the network at a time, and let networks don't overfit. It turns out that the smaller a neural network is, the less it's able to overfit. Why? Well, small neural networks don't have much expressive power. They can't latch onto the more granular details, noise that tend to be the source of overfitting. They have room to capture only the big, obvious, high-level features. This notion of room or capacity is really important to keep in your mind. Think of it like this. Remember the clone analogy? Imagine if the clone was made of stacky rocks the size of dimes. Would that clone be able to make a good imprint of a folk? Of course not. Those stones are much like the weights. They form around the data, capturing the patterns you are interested in. If you have only a few larger stones, they can capture lines the detail. Each stone instead is pushed on by large parts of the folk, more or less averaging the shape. Now imagine clay made of very fine-grained sand. It's made up of millions and millions of small stones that can fit into every nook and cranny of a folk. This is what gives big neural networks the expressive power they often use to overfit to a dataset. How do you get the power of a large neural network with the resistance to overfitting of the small neural network? Take the big neural network and turn off nodes randomly. What happens when you take a big neural network and use only a small part of it? It behaves like a small neural network. But when you do this randomly over potentially millions of different subnetworks, the sum total of the entire network still maintains its expressive power, right? So why dropout works? Ensembling works. Dropout is a form of training a bunch of networks and averaging them. Something to keep in mind. Neural networks always start out randomly. Okay, I didn't know that before. Why does this matter? Well, because neural networks learn by trial and error. This ultimately seems every neural network learns a little bit differently. It might learn equally effectively, but no two neural networks are ever exactly the same. Okay, it's just like the human. Every people is different and every thought is different. Unless they start out exactly the same for some written or intentional reason. Okay, it can never happen to humans. This has an interesting property. When you overfit two neural networks, no two neural networks overfit in exactly the same way. Overfitting occurs only until every training image can be predicted perfectly, at which point the error equal to 0 and the network stops learning, even if you keep iterating. But because each neural network starts by predicting randomly and then adjusting its weights to make better predictions, each network inevitably makes different mistakes, resulting in different updates. This culminates in a cure concept. Although it's likely that large, unregularized neural networks will overfit to noise, it's unlikely they will overfit to the same noise. Why don't they overfit to the same noise? Because they start reasoning, and they stop training once they have learned enough noise to disambiguity between all the images in the training set. The NNIST network needs to find only a handful of written pixels that happen to correlate with the output labels to overfit. But this is constructed with perhaps an even more important concept. Neural networks, even though they are randomly generated, still start by learning the biggest, most broadly sweeping features before learning much about the noise. This takeaway is, if you train 100 neural networks, if you train that, or in naturalized reasoning, they will each tend to latch onto different noise but similar board signal. Thus, when they make mistakes, they will often make differing mistakes. If you allowed them to vote equally, their noise would tend to cancel out, rewarding only what they all learned in common, the signal. Okay, then that makes sense. That makes sense now, because if they generate different mistakes or they try to get different noises, then if we they will have the same signals. Every layer will get they will all get core informations. Then how about we just drop out 50% of the information, and in the end, as they they will always keep the core information. They will absorb noises based on the common information or signals. Why don't we just drop out 50% of that information, and in the end, what we left is the signal that we want. Dropout in code. Here's how to use dropout in the real world. In the NNIST classification model, let's add dropout to the hidden layer, such that 50% of the nodes are turned off during training, randomly turned off during training. You may be surprised that this is only a 3-line change in the code. Following is a familiar slap from the previous neural network's logic, with the dropout mask added. Now let's give it a look. I equal to 0, layer 0 equal to the input imaging. Dropout mask equal to np or numpy.return integer, and we're gonna give it the shape. Give it a shape from 2 to the. Okay, I don't know how they did that. The layer 1 equal to the dropout mask times 2, and the layer 1 delta equal to the dropout mask times that. To implement dropout on a layer, in this case layer 1, multiply the layer 1 values by a random matrix of 1 and zeros. 1 and zeros. Okay, let me think about it. 1 and zeros. Okay, if here we set the real number to 2, as you can see here, if we set it to 2, actually it means we want to get integers from 0 to 1. It can be 0 or it can be 1, with the size of the layer 1 size or layer 1 shape. So we will get ones or 1 or 0 with the shape of that layer 1. Good. This has an effect of randomly turning off nodes in layer 1 by setting them to equal 0. Note that dropout mask uses what's called a 50% Borderly distribution, such as 50% of the time. Each value in dropout mask is 1, and 1 minus 50% equal to 50% of the time. It's 0. This is followed by something that may seem a bit peculiar. You multiply layer 1 by 2. Why do you do this? Remember that layer 2 will perform a weighted sum of layer 1. Even though it's weighted, it's still a sum over the values of layer 1. If you turn off half of the nodes in layer 1, the sum will cut in half, so you have to do some operations to try to keep it with the original size. Thus, layer 2 would increase its sensitivity to layer 1, kind of like a person learning closer to a radio when the volume is too low to better hear it. But at the test time, when you no longer use dropout, the value would be back up to normal. This throws off layer 2's ability to listen to layer 1. You need to counter this by multiplying layer 1 by 1 over the percentage of turned on nodes. In this case, that's 1 over 0.5, which equals 2. This way, the value of layer 1 is the same between training and testing, despite the dropouts, even if we did the dropout operation. Here's the final version when we add the dropout operation in our code. Dropout evaluated on MNIST. If you remember from before, the neural network without dropout previously reached a test accuracy of 81%, because falling down to finish training at if you remember from the before, the neural network previously reached a test accuracy of 81% before falling down to finish training at 70% accuracy. When you add a dropout function, or when you add the dropout function, the neural network instead behaves this way. As we can see, the test where is the test arrow? Okay, it is at the first column of the data. As you can see, the test arrow is going down. It's going down as the training goes on, and the test accuracy is getting bigger and bigger with the time goes on. Not only does the network instead pick at a score of 82%, it also doesn't overfit nearly as badly, finishing training with a testing accuracy of 81%. Notice that the dropout also shows down training accuracy, which previously went straight to 100% and stayed there, but now it is not. The training accuracy will stay at the 0 line. This should point to what dropout really is. It's nice. It makes it more difficult for the network to train on the training data. It's like running a marathon with weights on your legs. It's harder to train, but when you take off the weights for the big race, you end up running quite a bit faster because you trained for something that was much more difficult. Batch gradient descent. Here's a method for increasing the speed of training and the rate of convergence. In the texture of this chapter, I'd like to briefly apply a concept introduced several chapters ago, mini-batched stochastic gradient descent. I won't go into too much detail because it's something that's largely taken for granted in neural network training. Furthermore, it's a simple concept that doesn't get more advanced even with the most state-of-the-art neural networks. Previously, we trained on we trained one training example at a time, updating the weights after each example. Now let's train 100 training examples at a time, averaging the weight updates among all 100 examples. The training or testing output is shown next, followed by the code for the training logic. Notice that the training accuracy has a smaller trend than it did before. Taking an average weight update constantly creates this kind of phenomenon during training. As it turns out, individual training examples are very nice in terms of the weight updates they generate. Thus, averaging them makes for a smaller learning process. Okay, now I get it. It's kind of like if you want to exercise your math skills. If you want to do some exercise on your mathematics, you would like to solve one kind of problem with a set of problems. So you will get a better understanding on that kind of problems. Let's see how he just did that. At the first, he defined a variable len, which is batch size. It is equal to 100. Then the iterations equal to 300. For j in range of iterations. For I in range, we will get the length of the images, which is how many data we got, and we divided that by each size, so we can get the parts that how many times we need to trim for each batch size. And for each batch size, we instead of only using one images, we will use a series of images. But there's one thing that I couldn't understand, why he still using the same weights for doing this operation. Besides, as long as we are using a batch size of images as input, the output should be also a series of outputs. It is equal to the batch size, and everything else it is the same. The first thing you'll notice when running this code is that it runs much faster. This is because each np dot function is now performing 100 dot products at a time. CPU architectures are much faster at performing dot products batched this way. There's more going on here. However, notice that alpha is 20 times larger than before. You can increase it for a fascinating reason. Imagine you were trying to find a city using a very wobbling compass. If you looked down, got a head, and then ran 2 miles, you'd likely be way off course. But if you looked down, took 100 hand and then averaged them, running 2 miles would probably take you in the general right direction. Because the example takes an average of a noisy signal, the average weight change over 100 training examples. It can take bigger steps. You'll generally see benching ranging from size 8 to as high as 250. Generally, researchers pick numbers randomly until they find a bench size or alpha pair that seems to work well. Summarize. If this chapter addressed 2 of the most widely used methods for increasing the accuracy and the training speed of almost any neural architecture, in the following chapters we will pivot from size of tools that are universally applicable to nearly all neural networks, to special-purpose architectures that are advantageous for modeling specific types of phenomenon in data. Okay, it seems like in the next chapter we will go into a more advanced domain. We will get to know the activation functions, which I have no idea before. Okay, we will see that in the next video. Bye.